Well, one of the other things about the I don't know if it was the 29,000 or another chip that you worked on, but we also briefly, I think in the past, talked about register windows. Were those on the 29,000?
Yeah, that was on the 29,000. So
okay,
it's interesting. I've wondered. So the comparison is, so there were two processors that used a rolling window of registers that the execution stream is busy modifying. And one way, the term we used, and you'll have to forgive me a little bit because we're talking 37 years ago, right? So it's been a little while since I worked on this. Right. Someone commented to me that as you get older, you talk less about the great things that you'll do in the future and more about the great things you've done in the past. So I'm clearly in that in the older category, and some of it the memory fades because it's back far enough. But
right.
So one of the things that was part of the 29,000's architecture well before a lot of work had been done before I arrived. A lot of work. And one of them was that that there'd be this register window. And so basically what a register window is it says that all the registers live in memory. Right? And there were processors before the 29,000 that did that. Among them was the Texas Instruments 9900, which dates from the 70s, except it really had all the registers sitting in memory. Right? So kind of slow, right?
Right.
The register file in the 29,000, we referred to it as a stack cache. So it's and there is, well, that for the purpose of this discussion, we'll say there's 128 registers. There isn't. There's actually 192. It was originally 256, and we ran out of room. Right. So originally, because we had 8-bit fields, right, it was intended to index into the register file with 256 registers. Well, it turns out the chip design guys couldn't build the chip because there were too many registers, and so something had to go, and we ended up throwing away 64 registers. And so we have a lower half of 128 registers and the upper half of 64, which used to be 128, right? So there's a negative optimization because we ran out of silicon, right? And that then propagated to every member of the family afterwards. Okay, so the 120. So let's talk about half of the register file that was still there, right? It was 128 registers. Nominally, the stack pointer is a pointer somewhere into those 128 registers. And all the registers above that pointer position are parts of the stack that haven't been touched yet or are stale from previous execution. And the stuff below the stack pointer is active stack frames that we plan to look at as we unroll the stack. Okay, so the register file, 128 registers, is like a barrel. Right? You have a pointer that says, here's where I am in the 128 registers. There's a marker that says, this is the first of the valid registers, and so there, up to the stack pointer, is the top of stack with n registers. And then you have, from there, you wrap around to that same boundary pointer, which are the registers that you could use because the cache is sitting there. You just haven't dug deep enough in your subroutines yet.
Right.
Okay. So when you want to do a subroutine call, you compare the current stack pointer, bottom 7 bits, to the boundary register, bottom 7 bits, and you say, do I have enough room to allocate the registers that I need for this function, right? So the compiler optimization already knows I'm passing 3 parameters plus a return address plus a frame pointer or something, and they're all going to get pushed on the stack, and then we're going to jump off to the subroutine. So I need 7 registers. Are 7 registers available above the current stack pointer, right? And you look at it, says yes, there are. So you just update the frame register, you update the stack pointer, you put your parameters into the appropriate places in the stack cache, and you go to your subroutine, and it can then do indirect or offset references to the new stack pointer to get its parameters off the stack. And if it wants to call another routine, it does the same calling convention.
Right.
Eventually, if you just keep digging down, right, deeper and deeper into a subroutine call tree, eventually there won't be enough registers.
Right.
The registers that are furthest away, which are right at that boundary register, but looking at it from going backwards, those are the ones you're not going to want to look at for a long time until you unwind the stack. So you flush them out to real memory.
Right.
Okay? That's called a spill, right? And you just move the reference pointer, right, to however many registers you threw away, and now magically you've got more stack, right? So the cost of doing a spill, which is when you're digging down through the subroutine tree, right, is the cost of writing the registers out and updating the pointer. And you have a choice when you design your compiler or when you design the ABI for the processor of whether the spill is only as many as you need or spill everything, not a good choice, or maybe spill half. Right? And I don't remember, we certainly didn't spill only as many as you need, and we certainly didn't spill everything. I think the default was you just always spill half. Right?
Gotcha.
So you spilled 64 registers out to memory, and then you continued executing code. Now eventually you start executing return instructions, and eventually the frame pointer is pointing back before the reference pointer, which says the registers you want aren't in the cache, right?
Right.
And so now you do a fill, right? So you're unwinding the stack call, so now you do a fill, and the fill is bring in 64 registers.
Right.
Right? And so nominally the stack pointer is always in the middle with 64 registers behind it and 64 registers after it. And so again, we ran, and when I say we, I mean not me, we ran benchmarks and code traces, right, to figure out that whatever it was that the spill and fill quantities were, they basically meant that a very high percentage of subroutine calls triggered neither a spill or a fill. Right? So you had something like 95, 97% of subroutine calls didn't trigger a spill or a fill. So the efficiency was outstanding. Right? So you always had the top of stack, right, which had all your subroutine parameters or return values or whatever, are just always available in the fastest memory the chip has, right? The register file.
And so that's a an optimization versus like some other register window strategies, but just to like compare to not using register windows, right? If you have registers that you need to preserve across a subroutine call, you have to have a function prologue or prelude where you're going to push it onto the stack. And so one of the things you're saving is all of those operations where you're manually pushing and popping things to stack. Right?
In fact, if you look at x86 code, right, or ARM code for that matter, because ARM has a similar problem, you'll see. Particularly for things that might end up being interrupt service routines, right, is they end up having to flush all the registers right, out to memory, because you need a working set. On the 29,000, you say, my interrupt service routine needs X registers. Can I just move the pointer and give it X of its own registers, and when we're done, we'll return them all. So absolute register numbers, they don't exist in 29,000 code. They're all what is the offset from the top of stack, and the top of stack is always on chip, not out somewhere in main memory. Right? It's somewhere within those 128 registers.
I did some analysis of I basically heard about register windows from learning about SPARC, and I was looking at x86 and ARM and now RISC-V, and I was curious why none of these newer, if you will, right? I mean, some of these trace back to before, but why they don't use register windows. And I did a bunch of reading. I ended up writing a blog post that kind of like went through some of the trade-offs. But I know I had briefly mentioned to you seeing a comment about SPARC register windows were perhaps not implemented quite as efficiently. Do you think that contributed to register windows not being included in subsequent architectures?
I don't think so. I think that the SPARC decision. So SPARC also has register windows that spill and fill. The difference between it and 29,000 is the pool of registers is smaller, and the allocation size is fixed. So it's when you enter a subroutine, the movement of the frame register is always by the same amount. Whereas for 29,000, it's optimized on a per function basis. So if you only need 3 registers, you only consume 3 registers. Whereas SPARC always consumes 12 or something. I don't remember the number, but whatever it is, because it always consumes a fixed amount, it's always over allocating, which means it's spilling and filling far more often than 29,000. And I would guess that the reason is because of the layout of their instruction didn't give them the flexibility of having a field as part of the call instruction that said, here's how many registers I need to allocate. Right. So in the 29,000, part of that subroutine call is the frame increment. Right. So, and that was because of the way that those bit fields were laid out. Was we had an 8-bit immediate field that you weren't needing for the subroutine call. Right. Or actually, it was the. How was it done? It was actually not the immediate field. It was the destination register field. Okay. Right. The one that was always available, and that left you with a 16-bit relative offset for how far away the function could be. So you could be up to 64K words of offset, right? Which was split 32K before and after the current PC value. And if you needed more than that, there was a different call instruction that said call indirect through a register. Right, which would have a 32-bit absolute address or a 32-bit offset from the current program counter. Right. Makes sense. So I suspect it was just a function of how the bits were laid out, and there was also an overhead that it required an extra 8-bit adder in a somewhat critical register access path. Right. So it wasn't without its own costs in the silicon implementation.